We want to control our loads based on how much power we actually have available. But how? I'm Anthony Moises, and welcome to today's Fronius webinar on load management with digital IOs. Today, I'm going to be looking through a load management system with you, and for that we're going to first look at what loads we can switch, what makes sense, and what we want to achieve with it. We'll look at the hardware, the installation, what components we need and how to connect them, and then we'll go into the software. What parameters can we set? What can we do? What possibilities do we have with thresholds, switching our loads on and off depending on the available power? All of that will be supported by use case examples so that we have a good practical aspect to it as well. When do we actually want to maximize our own consumption, the amount of electricity that we use of the electricity we produce in our PV system? Well, that is based very heavily on the question of the energy tariffs. If energy is very expensive when bought from the grid and we get very little in the way of feed-in tariffs, then obviously we want to use as much as possible ourselves and only feed in the surplus above that. For that, we have to look into sector integration. And in the sector integration, we see that we have loads in a household, such as our regular household appliances that we all know, our washing machines, etc. We also have e-mobility as a large and ever-growing block. For example, an electric vehicle or an e-bike that we might have to charge. The largest part of that electricity that we're going to consume will usually be used in the form of heating or in cooling our rooms. So they have a greater importance when it comes to our load management system. We therefore want to create a load profile. If we have a load profile, we can decide which loads we want to switch, and we can decide when to switch them, what makes sense, how do we save the most energy when it comes to drawing from the grid, and how do we use most energy from our PV system. As you can see here in light gray, we have a production curve, and in dark gray, we'd have the load profile. I've highlighted in red a large block in that load. That red block represents an AC system. The air conditioning was switched on when the homeowner came home and noticed that the home was already warm. A large section of that red area isn't covered by our production line. It had to be drawn from the grid. And so that we don't have to use expensive electricity from the grid, we want to move that load into a part of the day where we have sunshine. But sunshine might not be there all day, so we have to adjust to that curve. And we can do that using the smart integration of the IOs. Having decided which loads we want to switch, in this case our air conditioning system, we can therefore shift that switching period into a production period. Having done that, the further optimization would then be a third step, namely to store energy for peak consumption in form of a battery or in heat in a buffer. So what can we actually switch? What other loads can we switch with a load management system based on IOs? We can switch a simple circuit. Any device that we want that is time independent and can be switched at any point during the day to create a reserve. That might be, for example, an SG-ready heat pump. SG-ready heat pumps are ideal in combination with a PV system as they already have an input for that 12-volt signal. A heat pump will then switch into state 3 and increase the temperature that it generates by a few degrees, something we don't notice as homeowners or as inhabitants of a building, but something that we will notice when it comes to that energy bill at the end of the month, when we see that we didn't have to use energy from the grid during the night because we generated enough heat during the day. A further option would be loads that, for example, we use particularly when the sun is shining. That might be things like irrigation pumps, circulation pumps, or pool pumps. Particularly in the summer months and during the days when it's nice and hot, we'll be using those things more. So why not switch them on when the sun is shining? And the example I mentioned beforehand, air conditioning. If we consider the consumption curve of an air conditioning unit, you'll find that it almost perfectly matches a production curve. Of course, the sun is out, creates the heat, the sun is out and creates the energy we need to combat that heat. What components do we need? Well, hopefully in a PV system, we've already got an inverter. Our inverters are already equipped with the IOs that we're going to need. A Fronius smart meter is probably a good idea in most systems. We do recommend it. And for most functions, you'll need it. It'll also help later on with visualization of those energy flows, but you don't necessarily need it for some of the functions. You can get away without. The only additional component that we need is one relay per IO that we want to switch. We'll come back to that. First of all, the IOs themselves. The IOs are not an extra you have to buy. They are standard from factory. They're integrated in our data communication cards and they're available for your use. They're also very easy for you to use. We have plugs that are easy to remove. You simply have to stick the end of the cables in and replace the plug. A plug and play solution for you. And you don't have to choose between using the digital IOs or any of our other interfaces. It is simply another addition, another way of communicating with other devices. So let's come back to that relay I mentioned. The relays have a few very basic criteria. We are dealing with a 12-volt signal, so it has to be a 12-volt relay that will then switch your main phase. The sum coil power on snap inverters is 3.6 watt. Now, that sum power is for all the relays that you want to switch. So if you're using 3 loads with 3 IOs, you'll need 3 relays. The sum of their coil powers should be less than 3.6 watt. With the Fronius Gen 24 Plus series, we increased that to 6 watt, so you have more of a choice. Finder Series 19 is an example of relays you might want to use, but there are plenty of others by other manufacturers. We also have a white paper on the subject on our website. Where do we put that relay? Well, obviously the relay has to communicate via the 12-volt signal with the inverter. So that is the first direct connection. The relay then switches the line to your load, but we would recommend for most loads integrating a manual switch in addition. Let's consider the option of a pool pump. You don't necessarily want to come home in the evening from work and then have to wait until the sun hits your solar modules again before you can rinse your pump. You want to be able to press a switch and backwash your pump without having to wait for that load to switch. So how do we connect the IOs? Well, on the bottom of our data card, as I said, we have that plug. And on that plug, you'll find the IOs labeled as IO0, IO1, IO2, and IO3. Those are our 4 IOs that we want to use for load management. You connect them by going to the relay from the designated pin. We'll come to the designation of the pin shortly. Out with one wire to the relay and return back to GND ground to close that circuit. Now, creating those connections is best done with a shielded twisted pair communication cable, category 5 or higher. In addition to that, I would recommend that in systems where you use a backup system, particularly a battery backup system, full backup system, that you not use IO0 for your load management. We'll come to the reasons for it, but the IO0 is then designated for the backup power. Having dealt with the hardware, we'll move on to the software. we want to connect to the web interface of our inverter, where we will then go into the device configuration. And under device configuration, you'll find functions and IOs and the option of opening load management. If we open load management, we will see a drop-down menu. Now, the first thing we want to make sure we do is to activate the blue slider to ensure that this function is in fact activated. Otherwise, we'll create settings, not activate it, and the inverter won't know that it's supposed to use those settings. For each pin, you'll find defaults suggested in the drop-down. You have to activate each pin individually and designate the pin, and I recommend strongly that you use the default. The reason for that is in our instruction manuals and also the instruction manuals for all our compatible partners, we use the same defaults. That means that we don't have to work out why things aren't communicating with each other. We have a standardized system. Our tech support will also depend on these default pins being selected, so they have an easier time and you have an easier time when it comes to troubleshooting later down the line. Having selected the default for all of our pins that we want to use, and here again, I did not use our pin 0 on load 4. We then make sure that we have put that slider across again, just to make sure, always a good idea to check twice, and hit save. If we don't hit save, again, our settings get lost, so we'd have wasted that step and we'd have to go back and do it again later. You can do this step during the initial setup as well, or you can go in and do it at a later point if you're going to a system that has already been installed. We'll go back one menu and then go into energy management and load management. Now, this is where we start getting into the fun part of working out exactly how to set up our profiles. We see two blocks, priorities and rules. Now, we're going to look at the rules first and come back to the priorities later. If we open the rules and we click on the first load, then we get a window that opens up or a drop down that opens up. First thing we can do is we can add a name, a description for what it is that this rule controls, the load. And to the right of it, we have a drop-down menu. We can select between off, we can select between power production and power surplus. The difference between these two is fairly clear. The power production is simply what the inverter is producing. It takes into account none of the loads that are used in the household or in that system. It doesn't take into account whether you are already drawing power from the grid or not. It simply bases its threshold values on the power that is produced by the inverter at that particular moment in time. The power surplus, on the other hand, is dependent on having a smart meter. And then we get to see how much power surplus are we generating in our system. So that is having produced it in our inverter, having satisfied the loads in our system, how much are we actually feeding into the grid, or how much are we drawing from the grid. We'll look first at an example with power production. Now, for the power production, we're going to look at an example with a circulation pump, selected power production at the top, and then we get to look at these thresholds. We have an on and an off threshold. As soon as we go above the on threshold in our production, our load will then switch on. As soon as we fall below the off threshold, our load will switch off. And it will keep switching every time it reaches those individual thresholds. Thereby, when our surplus is high enough or our production is high enough, here the blue curve represents our production. Our load switches on and switches off as soon as our production falls below, in this case, our 500 watt line. We then also have additional settings that we can make. We can look at the duration. Now, under duration, we have a maximum duration per on signal. We have a maximum duration per day and a desired duration. Now, that is a desired minimum duration per day. The minimum duration per on signal, the first point here, is particularly interesting if we're looking at something such as here, a pump. Now, a pump is a mechanical component. It has a motor, and it shouldn't switch on and off too often. We'll put a lot of stress on the system. It takes a lot more energy to start up and get running. So it makes sense to set a minimum runtime. I've chosen 5 minutes here, but you can choose whatever length of time makes sense without making the interval too long that you'd be drawing from the grid if you have a sudden drop in production. The maximum duration per day makes sense if you don't have a secondary switch. So, for example, a float switch on a circulation pump that might be filling a cistern or a reservoir. You want to make sure that that pump doesn't just run all day simply because you have the power, but runs as long as it makes sense until your water has been circulated maybe twice, and then you want it to cut off, and you want to offer up the power for other loads or to feed in, despite the fact you might not be getting much for it. Every little helps. Then we come to the desired duration. Now, the desired duration is more or less a backup functionality, if you like, to make sure that regardless of how much PV power we generate in that 24-hour period, in that one day, that load will switch on regardless. And that is by the desired time, here set at 1800, I want to achieve a certain amount of runtime. So here I want to run the pump for 30 minutes by 1800. If the pump only switched on once because I reached that threshold once and it ran for 5 minutes because of my minimum duration per on signal, then at 25 to 6, the inverter will tell the load to switch on and use whatever power is available, be that apart from PV or apart from the grid. And that way we would here achieve a shortened runtime, despite the fact we'd have the surplus over a longer time, or the production over a longer time rather. We'd then be cutting to a shorter period and providing more energy for other loads. Having done that, if it's the only rule we're setting up, we'd hit save again, but we're going to look at a second example. In load 2, I'm looking at a power surplus load. So for that power surplus, I'm going to be using a heat rod, and that's a boiler at 2.8 kilowatt. Note that now, in our thresholds, we not only have an on and an off threshold. Yes, it's an on and off threshold, but we can choose between consumption and feed in. With consumption, as soon as I fall below a certain consumption, I would be able to switch on, or if I exceed a feed in, I'll switch on. Vice versa, when it comes to the off thresholds, if I exceed a certain consumption, the load will switch off. If I fall below a certain feed-in, then my load will switch off. So I'm always trying to see a more positive energy balance with my load management here. In this case, we have 3000 watt to switch on, feed in, and a feed in of 50 to switch off. So that might give me a curve something like this. In this case, this is a combined surplus and grid draw curve. So I have two switching phases here where I switch on and off. As soon as the threshold falls too low, my load has switched off in between. As we're dealing with a secondary load, my load 1 would switch on first. We'd then take the threshold higher, and as soon as I have a surplus above load 1, I'd switch on load 2. Load 1 switches off because of that maximum duration we had set, and then I still have more of that power available for load 2 until again the threshold is reached for load 2 and it switches off. Then we have the durations. Let's look at the durations again. Just briefly, because this is a heat pump, I don't have any mechanical parts, I don't have a motor, so I don't need a minimum duration per on signal. They can switch on and off very often. They're really quite good at adapting to varying production and surplus. We wouldn't necessarily need a maximum duration per day. What I would, however, say at this point is, whatever heat rods you use, it is extremely important that you put in a thermic switch. They have to have some kind of thermal switch because we're just providing power with this digital I/O. Now you want to protect that boiler, that buffer, whatever it is, from overheating. You have to use a heat rod with some form of thermal switch in addition. Maximum duration per day here would be if you have a very, very large buffer that could theoretically reach 60 degrees Celsius, and you're fine with it only reaching 40 if it doesn't manage in that period you have allotted. The desired duration per day is relevant here because you might want to heat up water for when you come home, regardless of whether you had PV power during the day or not. So if you want to make sure your boiler is charged by the time you come home at 1800, then you might say, regardless of the weather, switch on for 45 minutes during the day, achieved by 1800. That then might look something like this. You had a short on period during the day, and just behind that black L2 would be 1800, where it draws from the grid to achieve the warmth required. The priorities are the next block that we're going to look at. Now, the priorities are perhaps a little complicated initially. You have the ohm pilot and the battery listed here. Now, the ohm pilot, and the battery both work at very low outputs already. So they'll already start to charge even when you're only producing a small surplus. The load management, on the other hand, is switched by the thresholds. So if you have a load with a very high threshold, you won't reach that for quite a long time. If you put the load management at a higher priority than the ohm pilot or the battery, then as soon as that threshold is reached, then the load management will switch. But until then, you'll be using the battery and the ohm pilot. This might be the better setting for most residential systems, but it doesn't have to be, depending on your priorities. Within the load management itself, the load with the lowest threshold will switch on first, so effectively becomes a higher priority. And if two loads in that load management have the same switching threshold, then they will switch according to the order they appear in this rules list. So if load 1 and 2 had the same on threshold, then load 1 would switch before load 2 switched. So other ways we can use this. We can use it in combination with our feed-in limitation. We can try to achieve a higher yield despite having a low feed-in limitation, for example. We can look at a load limitation, so make sure we don't draw too much from the grid, possibly because our utility connection, simply isn't big enough to deal with a higher load. And we'll look at a scenario where we connect multiple heat rods as well. In combination with the feed-in limitation, we want to make sure that before we reach that dynamic load or that dynamic feed-in limitation in the inverter, we already start using more of that energy ourselves so that we don't reach that limit. I've assumed here in the example, as you can see by the name, a 4 kilowatt feed-in limit. Now I'm doing that with a 2 kilowatt heat rod, which should switch on according to the threshold at a feed-in point of 3.8 kilowatt. As soon as the feed-in drops to 1.5 kilowatt, I want my heat rod to switch off so that I'm again feeding in as much of those 4 kilowatt as possible. So I've put in my thresholds, and that would give me a switching time that would go twice in this surplus curve. Mark you, this blue line here is a surplus curve. And as soon as our surplus reaches 3.8, the load switches on, then switches off again as soon as we drop close to our 1.5. This would then be our actual feed in. And now I hope you can see why the surplus curve doesn't have to reach the 1.5 kilowatt mark to switch off. We're really looking at the feed in here, which is the gray curve, which jumps every time we have our load. The duration setting here is again on a minimum duration, which is switched off because we're dealing with a heat pump. The maximum duration is not particularly relevant because, again, it's a heat rod. We hopefully have that thermic switch, and a desired duration isn't set in this example because it is simply an additional buffer to maximize my use in my home without reaching that feed in as fast. Looking at the next example, which is a load peak reduction, we're going to shed a load once we get close to a maximum draw from the grid. For that, we're going to assume a charging station that we're going to deactivate, and we're going to set our thresholds to a consumption setting. So as soon as the consumption exceeds 2,000, sorry, drops below 2,000, we're going to switch on, and as soon as it exceeds 6,000, we're going to switch off. What we achieve by that is we make sure that we do not get too much draw from the grid, so we're trying to make sure that our load stays as close or as far below the 6,000 watt draw as possible. We have a curve here that represents the switch on when the owner plugs in a device, for example. As you see the peak consumption going down to a 6,000 line, the load switches off and our consumption reduces, comes closer to the 0 line. We still have a build-up of other loads in the household, then it drops off. As soon as it drops off and reaches that 2 kilowatt consumption, our load switches on again, doesn't reach the 6,000, so it can keep running, and then has achieved a duration that it should have, is unplugged again by the owner, and the load reduces. It is advisable to use a minimum duration in a setting with a charging station. Obviously, it will be dependent on what you're charging, but most charging stations need a period to communicate with the battery before they even start charging. So looking into that is certainly a good idea. The example of the boilers and multiple heat rods. We have several scenarios that we can go through. We have already looked at the simple example of switching a single phase, single heat rod, and that is fairly simple. We go from one digital I/O via one relay to our heat rod, which is then switched thermally. A second possibility would be in a building with multiple boilers, for example, where I have several single phase boilers or heat rods. So I might have a small boiler in a kitchen or in a bathroom. I might have an additional one in a garden. I have several of my boilers, each switched individually by a separate I/O via a separate relay. Our third example would be for a larger boiler where I have one multi-phase heat rod, where I then switch the individual phases of that heat rod via a separate I/O. That is, of course, an option, and that way I get more of a stepped solution where I can follow my surplus or production curve a little better and really get behind that curve using most of my energy available. Now we've worked out how we can use the energy, but we don't know how much energy we've used. In these systems, we do have a smart meter at the feed-in point, but we only know that we have produced a certain amount and that we've had a certain amount of feed-in. We don't know where that energy has actually gone. So in visualization, we could get a bit of a better idea of just how much energy we managed to save by using a digital I/O solution. That doesn't just apply to the I/Os, obviously, but we can integrate into the power line to a certain load an individual smart meter. If we do that, if we dedicate each one with a name, then in our visualization via solar.web, we can then see exactly which load used how much. And we'd see that when we go in to our dashboard, top left, we'd have our loads. So what advantages do we have? We can increase our self-consumption. We can optimize the PV usage in our own system. We have all of that as an automated system. It switches on when the sun is available, or if the load is too high, or if the load is used differently. We have a very high dependability of a system with a backup, more or less, because we can use that minimum duration, so loads don't get overlooked. You might not overlook your irrigation system in the garden because you still have that minimum duration per day, and it takes very little effort and very few additional components to implement these systems. What prerequisites do we have? Well, we need an inverter with a data manager 2.0 or higher, and we need a flexible load. Time flexible, can run anytime during the day and create that buffer effectively. Additional material, well, yes, we need some cables and we need the relays. With that, I will now ask my colleague Hans whether we have had any questions. Hans, anything you'd like to add?
Yes, well, Anthony, we have a few questions. First one was regarding the Fronius on-pilot. Why should we use the on-pilot, basically?
Okay. Well, the on-pilot has several advantages over the IOs when it comes to generating heat. The on-pilot can follow the production curve or the surplus curve a lot better and has a direct connection with the inverter. The use of IOs creates a stepped load profile, so it doesn't quite use as much of the energy. It doesn't communicate as intelligently with the inverter. Or do you have anything else to add to that?
That's fine. It's fine. Anthony, and there was another question regarding the privatization of the load management when you're using a battery and a watt pilot.
Okay. The Watt Pilot has its own setting in the Watt Pilot app where you can adjust where it falls in the prioritization. As you might have noticed, it doesn't appear in the web interface on the inverter. That is a separate setting you'd have to take in the Watt Pilot app itself.
Yeah, exactly. And the last question was regarding the smart meters. So how many smart meters can we connect on the Gen 24 or Snap inverters?
The connection is via Modbus. So if you're connecting multiple devices, you only have 4 addresses that you have per Modbus input. Now we do have 2 Modbus inputs, so it depends on what else you have integrated in your system and how many Modbus devices you have there.
Good, Anthony, this was the question. So we stay online with you. We still continue to answer your questions. Feel free to send your questions also in the next 10 minutes. Thank you.
And with that also from me, thank you for your attendance. I hope that that was informative for you. And as Hans said, feel free to still send in your questions. We'll monitor the chat for a little while still. And until the next time, all the best and goodbye.